Okay, thanks for coming to my talk, everyone. My name is Joe O'Donnell. Here's my contact info. I run a startup. I'm going to talk about AI today. Originally, I was planning on including some code, a working program that would work with a kind of weaker version of what I'm dealing with, but in the course of making my talk, I realized that I needed to take it a step further, so I'm still working on the architecture. I'll probably work a little bit more on this weekend, so if anyone's interested in, seeing the results of that, text me or email me during the conference. If we have enough time, we can take a look at another collaborative AI system from the Zooverse towards the end of the talk. So today I will argue that what I call the collaboration approach is what's needed to create nearly strong artificial intelligence. Strong artificial intelligence doesn't exist yet, and neither does nearly strong AI. Strong AI is a computer system that has a human level or greater thinking ability. Strong AI has proven to be remarkably difficult to create, and there is no evidence to suggest it will be created within our lifetimes. An artificial intelligence system beat the human champions of the Jeopardy TV game show in 2011. That AI system, IBM's Watson, is a type of weak AI, meaning it can excel in a niche area, but can't do much at all outside of that area. I argue that there can be and soon will be a third type of AI system, which I'm calling a nearly strong AI, which won't operate at a general human intellectual level, but can operate in a specific human job at not only a human level, but at a superhuman level. I believe that AI researchers have made a mistake in focusing on either weak or strong AI while neglecting nearly strong AI. The reason they have been neglecting this area is that a reasonable approach to create it has not yet been explained until this presentation you're hearing right now. What changed is that over the last couple of years, new research has come out on the nature of human intelligence. This research shows that social instincts and analogy are at the heart of human intelligence. Social instincts allow knowledge to be worked on by a team and passed on. Analogy is the process of relating, narrating, or expanding past concept to get an abstract grip on a new event or situation. You could call it a stretching and storytelling of past mental elements to create a new piece of knowledge, such as, look out, that elephant tiger is headed your way. The reason that conjures up the new conceptual picture of a giant tiger is because of social instincts motivating the stretching of two concepts to work together in the brain. We'll get back to this after covering the AI background. This research shows that the way towards a partially strong AI. Partially strong AI will ultimately be able to do the most important tasks that strong AI would be capable of. But unlike strong AI, there is a clear path towards its creation. The acronym NSAI sounds a bit like the name Nancy, and Nancy is easier to say and understand than NSAI, so that's what I'll call it, Nancy. Today I'm going to talk about what that new understanding of intelligence is, the state of AI today, and how to re-architect current AI tools and development processes to create Nancy. First, though, I will cover some historical context. And if you're wondering why I'm reading off my phone, it's because my laptop is specialized. It can only output to the screen instead of both the screen and the words, so I'm kind of improvising a bit. The future progress of medicine depends on Nancy because of three interrelated reasons: genetics research, systems biology, and the explosion of research papers. These three areas pretty much define what the future of medicine is ultimately going to be about. All three seem pretty likely to hit a bottleneck sometime soon without massive new levels of computer support. Despite a large amount of genetic research since the human genome was sequenced in 2001, fairly little new disease-curing work so far has come out of that. Research on human genetics seems to uncover new levels of complexity in how genes operate every year. In 2012, it was discovered that very large areas of DNA were previously thought to do little, called junk DNA, in fact do a lot. The level of complexity that exists in interactions between biological systems also seems to be a bottomless well. Sequencing the genetic code has turned out to be only the barest beginning in the massive research effort required to make usable sense of large portions of the human genome. More bio and medical research is generated all the time and increases every year. A very serious problem has developed in that there are now many papers produced, so many that a human being is incapable of even skimming them or sometimes even finding all the relevant past published papers that are needed for their new research work. The need or even requirement for computer-automated research work in these three areas is very clear. But there are so many levels of interconnecting complexity in genetic, system biology, and the English language that even in a cutting-edge weak AI system like Watson would pretty much not be up to the task. Nothing less than a near human level of capability is required to get the full job done in those three areas. Otherwise, human researchers will end up wading through countless thousands of research papers for the next couple hundred years or so before we see the full medical benefit of having sequenced the human genome. However, what if we had thousands or millions of human-level or greater automated scientists? Automated scientists who work 24/7 at full strength without coffee, have no egos, don't need funding, and work for about $20 a month in pay. Such an army of scientists would stand a chance of reducing that 200-year or greater time period to perhaps 50 years. And also a second army can be trained to function as biotechnology engineers to create the drugs using the knowledge created by the first army. So now to shorten this up to get it under an hour, I'll skip a couple slides where I denounce Ray Kurzweil, and then I'll get to the repeated failure of AI and lack of ability to predict when it will happen versus steps forward. We'll touch on the failures showing that theme, and another failure cycle is currently happening. If we don't break out of this failure cycle, as has happened in the past, many people will turn negatively on the promises made in past steps. That was just kind of a summation that 2 or 3 times over the past 50 years, computer scientists have said, hey, look, we're only about 10 years away from a human robot. Then they failed to make it. Then they lost their funding. And that's probably about to happen again. Because over the past 10 years, Ray Kurzweil and some other people have been making similar promises, and we're about to fail to reach that again. We've got 2 movies coming out, one called Her, one called Transcendence with Johnny Depp. So people are going to be expecting to see human-like robots pretty soon, but they're not going to get them. Then we're going to all lose our jobs. So we don't yet have Johnny 5. So what we need to do is, for the first time in history, get on a development path where we'll take steady steps forward. So instead of promising all or nothing, I'm going to outline an architecture where I believe we can take steady steps forward, showing progress each year. That way we won't be making grand promises that will kind of fail to keep. So let's take a look at the history of AI. And something to mention first is the importance of differentiating between Nancy and past hybrid AI approaches. All AI up till now has been weak AI, which means a kind of niche computer program. It can do certain tasks pretty well, but ultimately it fails to be able to reason in a general type of way. And that causes a serious problem, and multiple times in history, an AI system has gotten so far that it's kind of just not done much good after that, because it fails to make the transition to a truly general understanding of the problem it's working on. And AI researchers often confuse those two things themselves, weak AI and strong AI. And because of that, you'll sometimes hear them saying, hey, look, I made this new system that recognizes handwriting. Now we're going to have a humanoid in only 10 years, but it never happens because they fail to account for that hard step of generalization. So let's take a look at the AI history and see what we have to work with and trying to take that step into some true level of generalization. Okay, so the first step from the originations of AI to the early 70s focused on logic. Chess checkers and simple math theorem provers were developed, and the high point of this period was reached with the Shrdlu system from MIT. Shrdlu was pretty impressive. It could control the robot, it could move pyramids and boxes around according to your commands, and it gave people a big expectation that pretty soon we'll be able to tell robots what to do. But that didn't work out because Shrdlu was only limited to a very certain specific environment. So that's how it avoided the generalization problem. And you can see these words are an example of how it works. So the next step, so an AI winner occurred not long after Shrdlu. They lost their funding because they failed to keep their promises. But then they thought, well, what if we gave our logic systems a whole bunch of facts and knowledge? Then maybe we could take them further. So they developed what's called the expert system, which is kind of like a logic engine plus a database of facts. And expert systems were pretty good at working with specific areas, like the rice crop doctor, and there's a bunch of other examples. And corporations ended up spending up to about $500 million or so in the 80s on these types of systems. But they ran into a problem towards the end of the 80s. They basically stopped working past a certain complexity level, and they're also incapable of generalization. So they kind of fell out of favor, but the idea was kind of reconstituted in other programs like Wizards, IntelliSense. A lot of stuff that we now take for granted comes from expert systems, but if you notice, there's always a limitation to it. A wizard can never write a program for you, it can only do certain specific tasks, and that's because of the generalization problem. And another kind of related concept of the generalization problem is the combinatorial explosion problem, which means that once you get into a general area, there's so many possible combinations that the computer is incapable of searching through them. So it has to come up with some other way of dealing with it than a search. So the next era after expert learning in the 80s, after another AI winter crash, was machine learning. Machine learning has been around for a while in various forms, but it really started to develop towards the 90s, and it involves basically automated statistics. One thing about machine learning, and this is another thing about AI, the words machine learning, it gives you this idea that the machine is actually learning something. In reality, it's not like that. It's more like a statistic program that uses memory in a repeated way to kind of get some information out of a piece of knowledge. Like, for example, this is a typical machine learning example. You've got a bunch of data points, and it plots a line from those data points, thus giving a kind of estimated, linear formula for them. Okay, so here's another example of kind of a more advanced type of machine learning, and this was kind of the next step after machine learning, which is computational intelligence. Now, computational intelligence, the way I see it, is, I don't really see it as that much different than machine learning. I see it as machine learning with unusual types of data structures. So with a neural net, for example, the output of a neural net is often an answer that's kind of statistical. Like, for example, if you were trying to separate your customers into different groups to send them advertisements, you could use this type of neural net, and ultimately it outputs them in these three segments, and those segments are kind of like statistical groupings. And there's a few different techniques in so-called computational intelligence, but ultimately most of them are pretty similar. They're usually statistical-like approaches used with a kind of graph structure that kind of stores statistical knowledge and then is used with new information. So it's basically kind of like a certain kind of fancy machine learning. That's the way I look at it. And by the way, a lot of the things I'm saying today, they'd be considered controversial by many people, so I'm going to have a question, answer, and denunciation period, so you can denounce me. Okay, so neural nets, like many things in AI, get hot on and off. A few times in history, investors have thrown money at them, and guess what? They're throwing money at them right now. We've got Zuckerberg and friends who are investing in a new type of neural net, and the big claim to fame of this neural net is the thrilling rumor that it can draw the picture of a cow. So it looks at a cow, it forms the idea of what a cow is, and then can draw a picture of it. And for that, they're getting some crazy amount of money. They think it's a big deal, but I don't see it that way, because it's another example of a statistical type of technique. Similar in the past, neural nets were used for like handwriting analysis, credit card fraud detection, and this is the same type of thing. It's impressive, but it's more of a one niche area. They still haven't yet taken the step into generalization. And if we don't take that step into generalization, we're never going to get our computers to do the things we want, like invent new drugs for us. Because they'll just be in niche areas, and there'll be too many things to keep track of. So, whoops. So another new area that's kind of developed is, I hate to use this term, but big data. Big data is kind of a marketing term, but the thing about it is we've gotten so much more new huge amounts of data from websites, from just the age of the computerized internet, that we've now reached a point where a lot of problems we couldn't solve before, we can now solve them, because we just have enough data to statistically handle them. And Peter Norvig gave an important talk on this topic. So it's kind of almost like a new area of AI also, because it's giving us new capabilities. And big data is like red hot right now. Corporations are into it, all kinds of money is being thrown at it. But, like as with the other methods, it looks more impressive than it actually is. You can do cool things with it. You can get better spelling correction, etc. But you're not going to get a talking robot out of it. Okay, time for the Q&A period. Any questions? Yes. Denunciations. Like, in other words, how dare you defame neural nets?
Check.
Guys, can you try to speak in we got a mic for you, so that we can get it on the recording.
I signed up for a course, I didn't start taking it yet, called General Gameplay, and how does that fit into this? Is it like a probabilistic model?
Your course is called General Gameplay?
Yeah, it's like basically being able to write a program that, without preconceptions of how to play a game, you just give it a list of rules, and then it's got to learn, I guess, as it goes along. I haven't really looked at it, but I assume it's still Bayesian and machine learning type stuff.
Wow, that's pretty interesting. There's some common approaches to games, searching in chess and checkers.
Right.
Variations of game theory, Bayesian. So presumably it's going to use some combination of that. You'll probably, if I was making it, I would first look at the rules of the game. I would probably use a Prolog program to determine what the rules mean and try to categorize what those rules were intended to do, and then try to put it into a category. Do I want to search? Do I want to do something with game theory? Right. Or am I required to do something with statistics? Or worst case, I have to use all of them. And see, the thing about it is, those are pretty much your only choices. You know, there are no other techniques you can use. So you're going to end up using one of those anyway. So you'd basically take your best guess at it. In the worst case, you just make it random, like it just moves randomly. And you know, with a lot of games, just following the rules is a challenge. If you can just get it to follow the rules and just move randomly, you know, that alone is like kind of a big step. You know, that's the first step in writing a chess program.
Right, because I saw that apparently Super Mario World is NP hard, just being able to like find a path and not die, I guess.
I'm not totally following that. You're saying what again?
It's like it would be NP hard to
okay,
generate
NP
an algorithm that plays Mario for you, I guess.
Yeah. There, you know, the whole. That's the whole intractable problem. You know, that's the worst case of the combinatorial explosion.
Right.
You know, the combinatorial explosion, and you know, NP hard is like impossibly hard. Combinatorial explosion is just harder than your computer can deal with. But many problems quickly will step into NP hard. And you know, one thing about this is that a lot of this stuff, it depends on the study of algorithms. Just knowing what algorithm is feasible to use for a certain situation, like the famous, you know, Bridges of Königsberg problem. You know, you could attempt to be a math genius and try to solve it directly, or you could try some approximation method, you know. And most of the time, you're better off doing some kind of approximation. But yeah, you know, I'm very happy to hear you're taking that course. That's exactly the type of things we need to be doing. You know, we've had this great internet revolution for 20 years or whatever now, but most of our internet sites, they're like simple databases where we just look stuff up and add information. You know, when I started programming in the 80s, you know, I was trying to make a robotic girlfriend, and I got it to work a little bit, but not much. It was kind of like an adventure game. I usually lost, but you know, I was expecting to have something more real by now, and we still don't. You know, why not? We keep making this mistake of, oh, look how impressive this is, but we're not making the fundamental advances in making a machine that can actually have a general understanding and do general reasoning. So this is my attempt to allow us to do that. See, the big problem is a lot of the people working in AI, they're trying to make this huge leap, like straight into a humanoid. You know, I think that's the wrong approach. I think we need to find a way to do it step by step. Even if it's kind of rough and doesn't work the greatest, if we do it step by step, we stand a much better chance of succeeding at some point than we do now. Because for the past 50 years, we keep saying, oh, this'll do it, and it just never works. So to carry on, and thanks for your question, that brings us to Eureka, part of the modern trio of AI programs that gives us a little hope of moving into general understanding. Whoops. So the Eureka system was called the robot scientist. It was able to discover force equals mass times acceleration on its own after a few days of processing. It's a genetic algorithm plus math system. Given some data and a problem, it can find a math equation that solves the problem. Its weaknesses are that it requires an exacting setup of the data and problems so it can work with them, and it can only work within the framework of its given data and problem. It was basically a minor improvement in the use of genetic algorithms, which is a type of computational intelligence. But minor improvements are very important in AI because much of the time there are no real improvements being made. The other factors that make it relevant to this talk is that it achieves a somewhat greater level of generality than other genetic algorithm systems by applying genetic algos to manipulate the symbolic system of math. So it's kind of a hybrid system. It does a couple of things. In other words, it has achieved a step forward in the ability to carry out analogy. Having a well-defined environment and goal also makes it an agent system. That was a type of AI that I skipped over. The so-called agent concept is a way of kind of organizing AI programs somewhat analogous to object orientation. And an agent system is something that has a goal and an environment and works towards that goal. And this is a step towards collaborative systems, which I'll explain some more shortly. So a fundamental problem with Eureka and AI today is that although it has a partial kind of analogy system, its analogy system is pretty weak. And it's also lacking in a conception system. It essentially has none. Reading critiques of Eureka is what partly led me on the path to this new idea of collaboration. Critiques pointed out that it doesn't have a system of conception, like it doesn't really think. It uses genetic algorithms, so it's more like kind of a random search that kind of evolves the search towards the goal. But one of the great things about Eureka, though, is that you tell it to do something, it keeps working on it while you're doing something else, and it'll eventually, get back to you. And I think that's an important part of AI, that too many systems now we expect instant feedback from, and that's kind of cutting off a large number of potential uses of computers and AI. We should get more used to asking it to do something and coming back like a few days later, because many problems, that's how long it's going to take. And kind of related to that, and part of my first version for collaboration is that we should get used to kind of communicating with the AI while it is processing, and it will communicate with us. Right now, it's a one-way situation where we'll ask it something specific and get the answer back. My first idea of collaboration, which is kind of weaker than the one I'm going to present more on today, it was simply the idea that, we need to give more direction while the AI is processing, and that's going to help guide the AI, and it's also going to help guide us. So make it more of almost like a human partner rather than a tool. So that brings us to our next advanced system called ML-Base, Machine Learning Base. ML-Base is a fantastic new system out of the Berkeley Parallel Computing Lab that aims to be a kind of database and wizard system for machine learning. It can be challenging to select the right machine learning algorithm to use for a given problem, to set it up and to interpret its results. ML-Base attempts to solve those problems, making it a kind of collaboration system. So it's pretty significant. There's a lot of powerful things that can be done with machine learning, but it requires a lot of knowledge to use some of them, and ML-Base helps to get around that problem. And it's collaborative because it attempts to help you to do that. So it's a step forward in the right direction, where the human and the AI are kind of working together to solve a problem. And that basic direction of the human and AI working together to solve a problem, there's other systems that have been going in that direction that I'm kind of leaving out. So it's a kind of general trend. It isn't a super strong set of steps towards collaboration, but there are steps in that direction. So we can see it happening. And they mostly came about by trial and error on what works, rather than kind of a concept on, hey, let's go in this direction. So I'm the one who's saying, hey, let's have this concept of going in the direction of collaboration. So that brings us to Watson. It's a hybrid system that combines a hypothesis agent, a knowledge base, and machine learning. It gives a strong appearance when winning at Jeopardy to already be a Nancy type of system, but it's not. It's a supercharged weak AI system, the next step after Eureka. What makes it so impressive is that it seems to understand much of regular English. However, it doesn't really conceptually understand English. Instead, it's really good at using its hypothesis engine to make use of its knowledge-based machine learning to find the connection among English phrases that makes the most sense. If you ask it when is Alan Turing's birthday, it will find various phrases and words statistically associated with that sentence and which response is the most statistically likely to fit the given context of those words together. It's the most important AI system in the world today, and it has breathed much needed new life into AI. However, it would be a significant mistake to think that Watson is the future of AI, because it is still a weak AI system and also lacks a clear development path towards Nancy or any other nearly strong AI. Siri is also a great weak AI system with a focus on information lookup. However, in typical AI industry fashion, the marketing department for Siri overpromised, and that actually resulted in a class action lawsuit against Apple for false advertising. The suit was dismissed, but it's significant nonetheless. So Watson and Siri, it's yet another case where something impressive is giving people the impression that, hey, you know what? Watson actually understands Jeopardy questions, but that's not how it works. If we look at the diagram, you know, what it's doing is that it makes hypotheses about what the words mean, but those hypotheses are based on statistics, not conceptual understanding. So it's basically taking a guess at what you expect it to hear. So if I say, when is your birthday? You know, the last 1,000 people that asked that of someone else, they gave some date in response, like August 23rd. You can send me a card. So then it knows that a date is probably the answer, so it finds dates associated with Turing, and then it'll give his birthday. So AI for decades was trying to make a disembodied intelligence when the only intelligence we know, which is humans, exists in a biological context. I think that's been another fundamental problem with AI research. We're trying to make this godlike thing that doesn't have a body, doesn't have a context, and is just like this intelligence just floating around without an environment. But the only intelligence we know, human beings, we're much more biologically grounded than we've realized in the past. We're not just these Greek godlike creatures who go around doing whatever we want. We're driven by instincts, we're driven by social structure. There's a lot more that's predetermined about human beings than we realize. We have an intelligence, but it works within the already existing framework of human instincts. So that kind of gives the intelligence something to work with. It gives it some guidance, it gives it some motivation. And that kind of helps it to keep moving along. If we didn't have that, we'd be in caves studying philosophy, the same philosophy that we studied like 1,000 years ago. And who knows, maybe jellyfish or dolphins do that. So that brings us to the answer, which is given in two incredible books. I can't say enough that Social Conquest of Earth, wow, that's one of the most important books I ever read. It was a little bit boring because half the book is about ants, but you know that's an important part of the book. And The Making of the Mind is it's a theory about how the mind works by this author, and it is in the ballpark enough to kind of put some things together. So humans didn't evolve the teeth or claws of large cats or hyenas. In fact, a human is supremely physically unimpressive compared to almost any medium-sized mammal. What did we evolve to allow our survival on the savannah? Two things together, the ability to learn and the instinct to collaborate. That's what makes humans different. That's why we can beat hyenas. One hyena could kill everyone in this room in about 5 minutes. You know, their jaws can snap bones. Yet, hyenas lived not too far from where early humans lived. So how on earth did we beat hyenas? Well, we did it with our learning instinct and our collaboration instinct. Humans are naturally curious. They want to figure out how things work. But also, just as strongly, we want to work together. So we'd see a hyena, we'd watch how it moved around, its behaviors, and we'd make a plan on how to defeat it, and then we'd work together to defeat it. It's pretty amazing when you think about it, because a human is incredibly unimpressive compared to any other creature in Africa. Our jaw it has no chance of killing an animal. We don't have a strength to kill animals. Without tools, without collaboration, we're totally helpless. Yet, those tools allowed us to conquer every other animal. So, let's take a look at some quotes from The Social Conquest of Earth. Meat and campfire are not enough by themselves to explain the rapid increase in the size of the brain that occurred. For the missing piece, we can turn, I believe with some confidence, to the cultural intelligence hypothesis of Michael Tomasello and his co-workers in biological anthropology, developed during the past 3 decades. These researchers point out that the primary and crucial difference between human cognition and that of other animal species, including chimpanzees, is the ability to collaborate for the purpose of achieving shared goals and intentions. Like, in other words, we're not these huge geniuses compared to chimpanzees that everyone thinks we are. The real difference is collaboration and learning instinct. And that's kind of this new idea that these anthropologists have discovered. So here's some more examples. This is paraphrased from page 227 of E.O. Wilson's book. Human children will attempt to help an adult having trouble opening a box. Young chimpanzees will not attempt to help other chimpanzees open a box. Humans have a very high level of collaboration, instinct, and sensitivity. Now here's the kicker. Chimpanzees have intelligence test scores about the same as 2.5-year-old children. Chimps and toddlers show the same level of skill in solving spatial problems, like using a stick to reach objects. But the toddlers show a much higher level of skill in learning from other humans by observing them. If chimps had more of a collaboration instinct, right now they'd have a culture similar to human beings. They would still have the intelligence of a 2.5-year-old child, but if you can pass intelligence on with each generation, then knowledge builds up. Our minds today are, we're like spacemen compared to the human beings of 50,000 years ago. If you took a human being from 50,000 years ago, they'd be living almost like an animal-like existence. They might be drawing on the walls, etc., but they would see spirits everywhere. They would be running around chasing after animals constantly to eat. They'd be almost little more than an animal. So what made us different was the ability to pass on knowledge and build it up over time, and the fact that our brain is programmable. We programmed our brain with culture to be something today totally different than what we started out with. So humans, it appears, are successful not because of an elevated general intelligence that addresses all challenges, but because they are born to be specialists in social skills. They are born to be specialists in those social skills by cooperating through communication and the reading of intentions. Groups accomplish far more than the effort of any one solitary person. So AI researchers, they've been focusing on this idea till now that, we're going to make this like godlike awesome intelligence. It's going to know everything. But our only example of intelligence, human beings, that's not how we got intelligent. We got intelligent by collaborating, by working with each other. Each person learns a little bit of knowledge and passes it on with communication. So on page 228, he points out that Homo sapiens approached the highest level of social intelligence when they acquired a combination of 3 particular attributes: shared attention, high awareness of the need to act together, and a theory of mind, which means the recognition of the mental states and the ability to communicate with others. So now that brings me to the second book, The Making of the Mind by Ronald T. Kellogg. This adds some additional points on how the mind functions. And some important parts of the mind are emotions and instincts. Humans carry out behavior because of a framework of emotions, instincts, and perceptual systems. And I think I'll speed this up a bit because I'm starting to run low on time. I think you pretty much already covered the framework of emotions and instincts.
You got about 10 minutes. You're good. Go on.
Okay, thanks. So then we have the next one of language and analogy. Here's another important point I would like to make, which is a modification of what Kellogg says in his book about language. I think a missing key on language and the ability to have conceptions is that language and conceptualization is grounded in body sense and perception data. In other words, I know what the difference between a small tiger and an elephant tiger is because of the experience I have had with my eye in perceiving objects of different size. And the words large and small have become associated with that. More abstract language concepts may arise from the self-observation of the working of one's mind rather than purely external perceptions. So the way to give computers the ability to conceptualize is to link both instincts and the experience of sensor perceptions to its knowledge base. The knowledge base should not be disembodied as it commonly is now, but instead based on the artificial social instinctual grounding artificially built into the computer system. A great AI scientist, Bostrom, said recently that he believes that analogy is the key to intelligence. Analogy is great, language is great, but we haven't really been able to get computers to truly understand them. Why not? Well, I think it's because they lack a grounding in a framework. That's kind of the missing element. We think language is this godlike thing, but it's really not. It's reference to past body sensation, so it has a grounding in an environment. If I say I'm walking down the street, you know, my mind associates that with I, my identity, body movement, and the perception of the street. So I'm actually building a kind of narrative story in my mind. So there's something there. It's not this invisible thing that it has often seemed to be when trying to get language to work in computers. An analogy is an advanced use of a concept. It's the taking of one concept and stretching it out so it becomes a new concept. I think when concepts are looked at as an organization of perception experience or internal processes, okay, I just covered that, I think. Steve Jobs had something important to say about analogy. And I had a slide for that, but I didn't include it. But what he said was that Bill Gates could really use a hit of LSD. Now, maybe that's true for a variety of reasons, but what he meant by that is the way to get creative with computers is to combine multiple senses together. When the Mac GUI opens up, it pops up in such a way that it looks like an object is coming towards your face, and then it's, you know, right in front of your face. And it makes sounds when it pops up. But it's not a physical object, it's a representation. So it's tying into other senses and making use of them. And LSD does similar things. It kind of ties senses together. And that's kind of what an analogy is. It's the taking of a perception and it's just stretching it out to mean something else. Like, I saw a tiger elephant. Well, what is a tiger elephant? You know, it's a very large tiger. And without analogies, computers won't have the ability to be creative and to reason. They won't be able to think, well, what if I take this molecule and turn it like this, similar to this other molecule, so it fits into you know, a receptor site. That type of thinking is that type of ability is what's needed to reason. So the next part, the inner interpreter. Humans have an inner interpreter of their own internal narrative. In other words, they talk to themselves internally as if they were talking to someone else, and thereby carry out their own thinking. Internal thinking is very close to being the same thing as external collaboration, but done with oneself instead of someone else. And that's another important critical part of collaboration. Most of the mind seems to hinge on both analogy and collaboration. You know, I'm thinking, gee, what seminar should I go to later? Well, I know there was one on Big Dad, but I missed that. I know there's one on sexual harassment or something. I'm kind of afraid to go to that. perhaps I should go to the electronics workshop. You know, so I'm kind of asking myself questions. And I'm carrying on a conversation with myself. So it's like two people are talking. I'm collaborating with myself. So the same thing we use to talk with other people, we're doing it internally. So that's the secret to narrative. It's collaboration. Make collaboration work internally, now you've got some thought going on. And another interesting thing about this, and the thing that made me upgrade my project from a weak AI niche to an attempted strong AI, or nearly strong AI niche, is that I realized that conception, analogy, and collaboration are all closely linked. If I want to share my mind state with someone else, I have to have the ability to have a concept, so I can share that with someone else. And so I can receive their concept when they communicate it to me and understand it. And I think that is another really big piece of what has made strong AI so hard to make. And this really is a big question, because the smartest people in the world have been trying to make strong AI for 50 years, and they have totally failed. They're not even close. You know, so this is one of the biggest science problems, at least the way I see it. I think that one of the big problems is that each part of intelligence is so closely linked together that it's almost impossible to separate them. And because it's impossible to separate them, it makes it either all or nothing. You have to develop the whole thing at once, or you've got nothing. And most other problems in science and engineering aren't like that. With a plane, we have the engine, we have the wings, we have the control surfaces. We can make each one differently. But now with intelligence, everything is mixed up together and it's hard to separate it. So if we can figure out how to separate the parts even a little bit, that's a really big deal, because then we can work on the parts individually, and that's a lot easier than making one huge thing together. So my attempt at this architecture is an attempt to separate the parts and separate the interfaces, at least to some degree. And that brings me to another point about this. It's critical to make an AI architecture that we can take one step forward at a time. It's impossible to make a human like a computer in even probably 10 years. It's going to require step after step after step after step. What's missing is a framework where we can develop it gradually. So that's what I'm providing here, the framework to develop it. And I haven't made my first working iteration yet. Hopefully I'll get something done by the weekend. But that's the general idea, you know, that the framework makes sense as a working model of intelligence, and to develop it step by step. So here are the parts of Nancy: learning instinct, collaboration instinct, and those are the two most important things: body sense, perceptions, and mirror neuron self-sense. Now what that third one gives us is an organization of the learning instinct and the collaboration instinct. In humans, the way my mind operates, I think, what do I want to do today? Well, if all my regular instincts are satisfied, like I have slept, I have eaten, etc., then I will go to my next most important goals, which is usually something involving social relating. And that social relating involves a sense of myself. Like, you know, who am I? Well, right now, I'm a single guy. Well, it would be nice to upgrade my self-image to be not a single guy, so I guess I'll try to talk to some women. That's also tied in with collaboration, because how do I get someone else's mind state in my mind? I do that by kind of temporarily taking on their self-image. And this relates to mirror neurons. If someone walks up to me and looks at my face, I see their face, and if they're angry or something, then, you know, my mirror neurons, certain neurons in my brain, which you may have heard about, will automatically take on the signaling of anger. So I know this person is angry. Like, my face will automatically mimic, to a certain degree, their facial posture, and that's how humans communicate emotions. So what we're communicating is a self-image. It's a temporary self-image, it's a changing self-image, but ultimately, if you want to communicate, which is the heart of collaboration, you have to have the ability to communicate self-image. In order to do that, you have to have a self-image. So we actually have to give this AI a self-image. So then we get into our basic mechanisms, and then we get into our concept, analogy, language, inner narrative, and mental time travel. And boy, I love to say that, mental time travel. That just sounds so far out. So here is the detailed architecture. This isn't the best diagram, but the fundamental parts are in the parentheses, and the interfaces are in the that other type of parentheses, whatever it's called. By keeping those two parts separate, it helps us to update each part individually, which is a key thing we're trying to achieve. So we can update them one iterative step at a time. So I'll say a few things about the other parts. The computer AI system's body is made of its processing system, memory structure, I/O, system library, and OS architecture. Its body sense is a representative reference of each of those aspects. And it's also connected to its self-sense. It has a set of organized representative references to its sense and narrative data as part of its self-sense. An intelligent entity's body and self can be in motion, but the fundamental grounding architecture of an entity's body and self does not change. In other words, your self-image kind of has a permanent part and it kind of has a changing part. So both of these factors will be a part of its body and sense of self. And this may sound like esoteric philosophy, but for reasons I hope I pointed out enough, it looks like this is something we have to do because of recent discoveries in how intelligence works. Its learning and collaboration instincts will be tracking, evaluation, and motivation modules that plug into the sense of self. This module will constantly ask the sense of self, are we learning to the maximum we can for this given day? And are we collaborating to the maximum we can for this given day? It works in 24-hour cycles. And that's another key decision too. Do you want it to say, am I collaborating to the maximum last minute, the last day, or the last year? If you say the last year, it's going to end up being a philosopher just thinking all day. If you say the last minute, it'll end up interrupting you constantly. Hey, how am I doing? But if you make it for the last 24 hours, then it's most likely to operate in a way that makes sense to a human being, because it'll be a kind of balance between the short term and the long term. So the self-sense instinct core will interface with the inner narrative layer. By implicitly forming base-level narrative and constantly injecting that into the narrative layer, it will also receive a certain amount of limited feedback from the narrative layer. And I see I have 6 minutes left, and I have many more paragraphs of detail on how the various parts of this architecture will work. But given the time, I think I'll just have to ask, is any Q, A, and D? Questions, answers, denunciations? Okay, well, I got to this slide a little early, but just to mention again, here's my contact information. If you'd like updates on the code, feel free to email me or text me, and maybe I'll see a few more things during my last few minutes on the details of this architecture. And by the way, the warm-up project was going to be at Zooniverse.org. That's an online semi-collaborative system used for science. You can get a sense of kind of where collaborative systems are going with that. But then again, that's a weak AI system, and I'm talking about a nearly strong AI system. So let's take a look at some of these parts in the last couple of minutes. The narrative layer will make narratives about the current situation, form potential future narratives, and evaluate which future narratives are desirable to work towards. The narrative layer forms both the current understanding of external data and debates and decides on the future course of action for the AI. In other words, the AI will have an artificial free will. A free will is necessary in order to allow the AI to carry out artificial creative thinking. And by the way, there's a bunch of AI researchers who are very afraid of free will. They're afraid the AI will run loose and eat us all or something. I'm not at all concerned about that because there's an AI contest going on right now. You know what the AI contest is for? To see if you can make an AI that can differentiate between a cat and a dog. If you can do that, you'll actually be famous and win a lot of money. So, I mean, does that sound like they're going to take us over? No. So the narrative layer will make use of the language concept analogy layer as it needs to create and or discover a narrative as driven by the self-instinct layer. In other words, the instinct layer drives everything, and the narrative layer is kind of like the planner and the understander of language. And the way the narrative layer works is that it plays out language statements using its body sense, just the way a human would. Well, not just the way, but kind of similar. In other words, it has its own little internal environment. It will carry out mathematically a person walking down the street. It has an internal sense of the physical world and logic. It carries out that narrative, then it looks at the resulting environment, and it'll say to itself, how does this affect my instinctual goals? If it's a positive, then it may choose to do it. If it's not a positive, then it won't choose to do it. So that's how intelligence works. It's a part of mental time travel. Language is kind of a database of pointers to different concepts: body sense, conceptions, and analogies. And it's kind of a logic description system. I think AI researchers make a bit too much out of language. It's like they confusingly combine narrative, concept, and analogy into language. But if you separate them, you're going to end up with 4 different things that you can actually work on, rather than everything kind of mushed together, which makes it impossible to work on. So that's one of the key parts too. Separate those things so you can take individual steps with them. So I said a bit on analogy language, and I said a bit on concepts. A concept is kind of like a unified body sense, narrative, or bit of language. It's kind of like a reference to a unit made up of those. So any questions on how any of these parts work? Yes? Yeah, the question is that am I saying that neural nets are not a way to move forward in AI? And the answer to that question, I think, is yes. It's correct. I don't think they are a way to move forward. Yeah. Oh yeah, that's a great question. Are the programming languages we have now sufficient to let us build an AI? And I think the answer is no. I think we do need new programming languages. And I'm a Lisp programmer, and Lisp programmers make domain-specific languages. We make a kind of custom language for the problem we're working on, and that's what I'm going to be working on. In other words, my language is going to have a concept object in it. We need a language with these parts in it so we can get them to work together. Because the languages we have now, they're too focused on either the process or various abstract things like an object. Like, how does an object relate to the mind? It's too lower level. We need something more mind-like. And I think these are the parts. So I think we build the DSL out of these parts, and we connect them together, and we experiment. Like, for example, right now, the Instinct module, it has just collaboration and learning. And the body sense model is pretty limited. But the human body sense is much more elaborate than that. You know, we have facial interactions, we have emotions, and we also have social hierarchy, which I haven't gotten into, but is probably important also. Like, in other words, if an AI is working with humans, you don't want the AI constantly interrupting, Linus Torvalds to ask him, like, minor questions. The AI has to understand his place and work accordingly. And that's an important part of social hierarchy, or, social effective collaboration also. So this is really only the barest beginning. I'm just saying that this is the type of architecture we should work on so we can take steps forward. You're welcome. Any other questions? Yeah, I think, so few people realize that neural nets are deceiving because they're very impressive. Watson is very impressive, but they're never going to be strong AI because they're too niche orientated. They could be completely excellent at doing statistical pattern matching. Like, in other words, it's seen a cow from 100 different angles, so it can detect statistically when an object is a cow. And then it knows how to draw. Well, thank you, everyone. I appreciate your attendance.